All right, so glucagon is another hormone that is secreted from the pancreas. It's also secreted from the islets of Langerhans, that group of cell that we mentioned, which forms a part of the pancreas, a part of the endocrine pancreas. And it's going to be secreted specifically from the alpha cells of those islets of Langerhans. All right, so the beta cells secrete insulin, whereas the alpha cells secrete glucagon. And just a quick histology lesson here. We typically aren't able to distinguish which cells are beta or delta, but we know that the cells around the periphery of these islets are what we identify as the alpha cells. Okay, so the alpha cells are usually around the periphery of this group of cells that we call the islets of Langerhans. But other than that, we can't really distinguish between the beta and the delta cells because they're all kind of clustered in the middle. Now, glucagon promotes glucose sparing for the nervous system, meaning that it's going to break down our storage forms of glucose, but it's going to do so in a way that really only focuses that breakdown for the nervous tissue. Our other cells can kind of tap into other biomolecules such as amino acids and triglycerides, but it's going to kind of shunt most of the glucose breakdown, kind of sparing that for the brain, which we know prefers glucose as its fuel, as its energy producing molecule, right? Some of the actions of glucagon are mobilizing energy stores. So that's glycogenolysis, the breakdown of glycogen from muscle and from liver to liberate energy. And then lipolysis, the breakdown of fats to liberate energy as well. It's going to synthesize new glucose from other sources. This is what we call gluconeogenesis. So gluconeogenesis is the process where we're able to make new glucose from other glycogen molecules, so things like amino acids and fatty acids. We can then synthesize some glucose from those as well. And this is what I mean by that glucose sparing for the nervous system. Our other tissues can tap into other reserves, whereas glycogenolysis is kind of spared just for the brain, the liberation of that glucose just for the brain. And then it's acting as a catabolic hormone in this way, as in it's breaking down biomolecules, liberating energy, and that is what the role of glucagon is in terms of its broad function. It's going to be secreted during the post-absorptive state. So think about, again, that those two analogies we talked about last time. Having just had a large meal versus having gone for a while without a meal, that is when glucagon secretion is increased. During our post-absorptive state or during the fasting state, when we have gone for a period of time without a meal. This is in alignment with the sympathetic nervous system. So the fight or flight response, we also see increased glucagon secretion here as well. And then that is also aligning with epinephrine. So these three things are secreted along that post-absorptive state: epinephrine, glucagon, and that is eliciting that fight or flight response. Whereas glucagon secretion will decrease during the absorptive or fed state. And if you think about it, that makes sense. If you just had a large meal, you're not trying to break down all of these energy stores. You're trying to do the opposite, right? So you're going to increase your insulin secretion, decrease your glucagon secretion if you've just had a large meal. But if you've gone for a period of time without food, you're going to increase glucagon and decrease insulin. Alrighty, and that is the antagonistic or comparative secrecy that we spoke about with these two hormones. So this is kind of an overview of what glucagon does. It's secreted from the alpha cells in the pancreas. In the liver, it's going to increase glycogenolysis, or breaking down glycogen to liberate glucose. It's going to decrease glycogen synthesis, right? We're not trying to store things during this period if we haven't had food for a while. It's going to increase gluconeogenesis, or the production of new glucose from other sources, increase ketone synthesis. So ketones are that kind of backup reserve that we talked about as a breakdown of fats to make some energy stores. It's going to increase protein breakdown or lipolysis, proteolysis, and then it's going to decrease protein synthesis. Again, we're not trying to store or put away energy reserves in this period. In our adipose tissue, in our fat cells, it's going to increase lipolysis and decrease triglyceride synthesis, okay? All right, so that's kind of the general function of glucagon. And this is why we speak about the fasted state of increasing glucagon secretion, or being in alignment with increasing glucagon secretion, because these are the types of functions that we want if we're going for a while without food, or if we're in the fasted state. Okay. So here we can speak about the regulation of our overall blood glucose and how both of these hormones kind of seesaw with each other in order to keep our normal blood glucose stabilized and regulated. So typically the body likes to be in homeostasis with a blood glucose of about 70 to 110 milligrams per deciliter. And that is a fasting blood glucose, by the way. So basically, if you haven't had a meal, right? You wake up first thing in the morning, you haven't had a meal overnight, your blood glucose should be somewhere around that 70 to 110. If you're having a higher reading than that, anywhere above 140 milligrams per deciliter, this brings us into hyperglycemia. So hyperglycemia is raised blood glucose even after a period of fasting. You still have got lots of glucose circulating in your plasma, even if you've gone for a while without bringing in food or bringing in glucose. And then we can also speak about hypoglycemia, which is a glucose reading less than 60 milligrams per deciliter, which is very low in terms of our energetic needs and our caloric needs and demands for our tissues, okay? So when we speak about insulin and glucagon, both of these hormones act to keep us at that normal blood glucose. If you haven't had a meal, your glucose still should not dip below 60. Glucagon should chip in and should help to keep your blood glucose between 70 and 110. If you've just had a meal, again, your glucose should still not go above 140. Insulin should chip in and help to keep your blood glucose below 110 within that normal range. And so when we see blood glucose readings that are outside of this spectrum, that are either hyperglycemic or hypoglycemic, this is where we begin to speak about diabetes, where we have imbalance of these hormones, or other endocrine disorders can bring about hyper or hypoglycemia as well. Okay. Right. So here we're looking at the effect of our plasma glucose on, or the effect that is brought about on our plasma glucose by these hormones. So on the left, we can see what happens in the presence of insulin. So insulin is secreted during states of increased plasma glucose. It's released from the beta cells in the pancreas that we talked about. In most of our tissues, we're going to uptake the glucose that we need at that time for those cells. In liver and muscle, we're going to increase glycogen synthesis or glycogenolysis, which is basically storing away excess glucose for later on. And then in the liver, we're going to decrease gluconeogenesis because we're not actively making glucose. Instead, we're storing up that glucose for times of need. And all of those things will result in a decrease in our plasma glucose. So insulin decreases plasma glucose. And when we say decrease, we mean it's going to take that glucose out of the plasma, out of the blood, and it's going to move it into the tissues, either into our cells to be used or into our liver and muscle to be stored, okay? On the other hand, glucagon is going to increase our plasma glucose, and the stimulus for glucagon secretion is decreased plasma glucose. So think about, again, you're going for a while, being in the fasted state, not having had a meal for an extended period of time. These are the types of functions that you're going to bring about. So let's kind of fill this in here. So first of all, we know this is being secreted from the alpha cells in the pancreas. Okay, and you can kind of fill this table in with me as we go. And the alpha cells in the pancreas are going to increase the secretion of glucagon. Righty. Now, that's going to do two things. It's going to do first, it's going to have an action in the liver. And then a second action is going to be in our adipose tissue. Okay. In the liver, it is going to increase gluconeogenesis and glycogenolysis. So gluconeogenesis, which is using other molecules such as fats and proteins to make glucose. And then glycogenolysis, which is breaking down glycogen to liberate glucose, right? So the big picture here is we're making glucose, either from other sources or from glycogen itself. And then in the adipose tissue, we are going to increase lipolysis, which is breaking down fats to liberate energy. And we break those down to fatty acids. So breaking down fats increases our fatty acids. And these two things are going to result in increase in our plasma glucose. In terms of the processes that take place in the liver. And then in terms of what takes place in our fat cells, this is basically going to spare glucose. Okay, so the fact that most of our other tissues can tap into glycogen and other stores to make glucose, we can use fats so that some of this glucose can be spared for the brain. So because we can tap into fats, we can kind of spare our glucose production to be used in the brain where we really need glucose